of providing growth, necessitating employment, skill sharing, and exploring further areas of research. And to promote these two fields, the state government has recently taken a lot of initiatives by introducing new academic programs in higher education institutions. And as you know, this machine learning, that's actually a science of programming computers so that they can learn from past experience in the sense of the data. So in machine learning, all of you know, data is an indispensable commodity. And the performance of a machine learning algorithm is greatly depends on the quality and the quantity of the data. And another beautiful aspect of machine learning is it uses the theory of statistics. And in my section, I'm concentrating on how the concept of statistics can be used in an effective manner for developing a machine learning algorithm. That is my topic of my presentation. And when we consider any machine learning algorithm, number of machine learning algorithms are there, and if you consider any machine learning algorithm, generalization is the idea used in almost all these machine learning algorithms to extract the knowledge from the data. And this is because machine learning algorithms recognizes various patterns from the data. So in order to generate those patterns, these patterns are actually known as the knowledge. And in order to generate those patterns, we need a huge amount of data. And with the help of these patterns, we can take any type of decisions. And that is the beauty of machine learning as well as the artificial intelligence. And conventional machine learning algorithms include a number of different algorithms are there. There is linear regression, logistic regression, naive-Bayes algorithm. I'm going to discuss the naive-Bayes algorithm. Then SVM, support vector machine, then radial basis function, then decision trees, ensemble learning, neural networks. A number of these type of conventional machine learning algorithms are there, and these algorithms are very efficient also. But recently, the conventional way of machine learning is changed with the introduction of a new paradigm, and that is called deep learning. And in conventional machine learning, to identify the features needed to train the algorithm, and that is a challenging task. That is a challenging time-consuming task. And in deep learning, this challenge can be minimized, or we can very efficiently solve this challenge by introducing the concept of neural networks. And again, when we come to the concept of neural network, it is very interesting to see that these type of neural network based architectures always use some simple linear algebraic operations such as vector addition and multiplication. And I think almost all the students already learned these concepts in their high school classes itself. And several deep learning architectures are available today to handle various types of problems like deep neural networks, then convolutional neural networks, then autoencoders. Hello? Presentation screen on ആക്കിയാൽ മതിയല്ലോ. Okay. So a lot of deep learning architectures are available today, like deep neural networks, then convolutional neural networks, then autoencoders, then recurrent neural networks, then generative adversarial networks, Then some pre-trained models like VGGNet, AlexNet, Inception V3, and all these architectures are popular in today's research. Because all these models we can very efficiently utilize for solving various type of problems, And recently, I used one architecture known as long short-term memory to predict the how many, for example, COVID-19 patients we have to expect in tomorrow. Tomorrow we have to expect how many COVID-19 patients using the data generated from December 2019 onwards, from the data generated from 2019 onwards. Or using the same architecture, we can generate the decision regarding how many patients we have to expect in the next week, how many COVID-19 patients we have to expect in the next week. So that our government can take necessary steps for arranging the necessary facilities for treating these patients. And these types of algorithms are very important in today's world to make such type of decisions, not only in the case of COVID-19, but in the case of, for example, for weather prediction, we need some efficient algorithms. And I hope that it is the responsibility of our students to generate these type of efficient algorithms for serving the community of the whole world. And with these words, I conclude my speech. Then we can directly move on to the presentation. So I don't like to take your time for discussing this type of general things. We can directly move on to the presentation. And also, thank you for giving me this opportunity for releasing this beautiful magazine. And in this occasion, I declare that the magazine is released. Thank you, Binimol, for giving me this opportunity. Okay. We can move on to the presentation item. Is it possible to see my slides? Hello?
Yes, sir.
No, presentation is not visible.
Not visible?
No.
Yeah.
It is showing it is presenting, but not at come.
ഇപ്പൊ കാണാവോ ടീച്ചറെ? കാണാവോ? ഹലോ ഹലോ ഹലോ
പ്രസന്റേഷൻ കാണുന്നില്ല സാർ.
ഇല്ലേ? എനിക്ക് പ്രസന്റ് ചെയ്യാനുള്ള പെർമിഷൻ ഉണ്ടോ? ഒന്നും കൂടി ലോഗിൻ ചെയ്യട്ടെ.
Now your PPT is visible, sir. Sir, you may continue. If it is not possible, it's okay. So now your PPT is visible.
Sir, mic unmute ചെയ്തിട്ടില്ല.
Sir, please unmute your mic.
Okay. Okay, അല്ലേ? Am I audible?
Yes, sir.
Yes, sir.
Slide visible ആണോ?
Yes.
Yes. Okay. This is the topic of my presentation, that is decision making, a machine learning approach. And in this presentation, I would like to discuss these topics. That is, what is machine learning, and what is probability, and what is conditional probability, then Bayes theorem, then Bayesian classification. Then based on all these concepts, how we can write a machine learning algorithm to classify a particular data set. And this is the agenda of my presentation, because I include these basic concepts because of the reason that in most of the machine learning algorithms, we use some basic mathematical or statistical concepts. And here I would like to discuss some basic statistical concepts like what is probability, what is conditional probability, and what is Bayes theorem, and all these are some basic concepts. So how these basic concepts can be very efficiently used for implementing a machine learning algorithm, and that machine learning algorithm is nothing but the Bayesian classification algorithm. And you know what is machine learning? As I said earlier, the science of programming computers so that they can learn from data. Okay, but here data is very important, and all of you know, in today's world also data is very important, and in order to get data, we have to pay a lot. Okay, so actually this data contains a lot of various type of knowledge, and how this knowledge can be extracted from the data. And that is the main objective behind any machine learning algorithm. But here, in general, machine learning can be defined in this way: the science of programming computers so that they can learn from the past experience or data. Programming computers or machine learning can be defined in another way like this: programming computers to optimize a performance criterion using example data or past experience. And every machine learning algorithm is associated with a particular performance criterion, that may be classification accuracy or error or the area under the ROC curve, etc., etc. A lot of different performance criterion is there, and to optimize the performance criterion. Then in the case of error, optimization means minimize the error. And in machine learning, data plays an indispensable role, and machine learning algorithm is used to discover and learn knowledge or properties from the data in the form of patterns. And the quality and quantity, as I said earlier, the quality and quantity of the data set will affect the learning and the prediction performance. So we have a huge amount of data, we get good knowledge. And if the quality of data is good, we get very good prediction results. Okay, and machine learning uses the theory of statistics inbuilt in mathematical models because the core task of machine learning is making inference from a sample, sampling theory, and that is very important in statistics. We have it is not possible to in our real world, it is not possible to consider almost all the various data available. And in order to process that huge amount of data, we have to spend a lot of memory in our computer, but it is not possible. So the easiest task is to collect a sample from that total domain and make the inference from the sample, make the results from the or knowledge from the sample, and generalize this knowledge is related to the population, and that step is actually known as it's a subset of the inferential statistics. Inferential statistics, I think you are aware with the inferential statistics, such as a number of different probability distributions, problems related to probability distributions, testing of hypothesis. I think all these things are aware to our students. Okay, but here the machine learning uses the theory of statistics in building mathematical models, because the core task is making inference from a sample. Okay, but here we have a population, but it is not possible to consider the different instances available in the whole population. So we take a small sample from the population, and based on that sample, we can generate necessary patterns. We can take the decisions, and after that, we can generalize. Generalize means we can say that, and this knowledge actually represents the whole population. Then in machine learning, two different type of data sets we have to use, and that is labeled data sets and unlabeled data sets. And the labeled data sets are always associated with the supervised machine learning task. And the machine learning is actually classified into supervised machine learning, unsupervised machine learning, reinforcement machine learning, then semi-supervised machine learning. And this is a broad classification of machine learning algorithms. And here I am going to discuss only the supervised machine learning algorithms. And in order to handle a supervised machine learning algorithm, we need a labeled data set. A labeled data set. So this is the mathematical representation of a labeled data set. X is equal to xn, where each instance of the data is composed of R components, that is a d-dimensional vector. D components are there. Okay, and this is the information with the independent variable x. Independent variable x, and in addition to that independent variable, we have a dependent variable, and that dependent variable is y. And in machine learning, this dependent variable y can be considered as the label. So this data set can be considered as a labeled data set. Labeled data set. But here we consider n different instances, capital N different instances, and this small n actually represents the number of features used for representing these samples. And here n features, sorry, d features are used because this is a d-dimensional vector. But here the first component of that vector represents the value of the first attribute, second component represents the value of the second attribute, etc. The last value, that the dth value, actually represents the value of the dth attribute. So this is a d-dimensional vector, and this is the label. Then in the case of unlabeled data, labeling information, that is y, that is the dependent variable, that is not available. But here x, capital X, represents the feature set containing n samples, and each sample is d-dimensional vector. D-dimensional vector, that means if we consider a particular sample, say nth sample, and that sample can be represented mathematically, we can represent it in this way: x1, x2, x3, xd, and all these are feature values of the nth sample. And this is the first feature value of the nth sample, second feature value of the nth sample, third feature value of the nth sample, and d, that is the dth feature value of the nth sample. Then transpose means that is this features can be considered as a column vector. And in machine learning, this vector can be considered as a feature vector. This vector can be considered as a feature vector. Okay, but here each column dimension of a vector is called an attribute or feature or variable. And attribute, that name is familiar to you because all of you are familiar with database management systems, and you know what is an attribute there. And the same concept can be applied in machine learning also. Attribute or feature or feature or variable. But here a feature, and that is a very popular term associated with machine learning. Machine learning attribute, that is a term associated with database management system. And here y stands for the label set known as a decision. Okay, but here in mathematics or mathematical, when we consider the idea of a mathematical function like y is equal to f of x, y is equal to f of x, and x represents the independent variable and y is the dependent variable. Okay, but here in machine learning, this y actually stands for the label, and it is actually known as decision, because when we provide a value for the independent variable x, with the help of that function, we can automatically generate an output value, and that output value, that is actually the y always depends on the value of x. And in this case, y actually records what decision or label a feature vector corresponds to. That means in the case of a patient data set, the y actually represents the name of the disease. And in order to predict the name of the disease, we need some values. We need some values, or we need some features, and these features may be symptoms, lab results, etc., etc. So when we consider a particular patient, and associated with that patient, we can assign a number of feature values like symptom number 1, symptom number 2, symptom number 3, etc. Then lab result 1, lab result 2, etc., etc. Then at last, associated with that particular patient, we can assign a disease value, and that disease value actually corresponds to the label. So a labeled dataset can also be described as xn that belongs to R. R represents the set of real numbers, and this is a d-dimensional vector. Then yn, that is a label of the nth patient, or the label associated, or the disease associated with the nth patient, and that is always a real value R. That means we can represent that information with the help of a real value or a nominal value, etc. And here, in symbolically, the data set can be represented in this way: xn, yn. And this can be considered as a data pair. And this xn, the component, the first component actually represents the features, and the second component, that is y, represents the label. So the concept of a data set is very important in machine learning. So there are two types of data sets: a labeled data set and unlabeled data set. And in the case of unlabeled data set, and that is normally used for unsupervised machine learning algorithms like classification, then association rule mining, then feature selection, etc. And all these are unsupervised machine learning tasks. And for supervised machine learning task, we need a labeled data set, and a labeled data set can be represented in this way: xn, yn. Okay, and y is the label. Then when again, in order to discuss with machine learning, we have to understand these two terms, that is training data set and test data set. Then and what is training data set and what is test data set? And in order to understand the concept of training data set and test data set, first of all, we have to understand the concept of universal data set. And I think all of you are aware with the universal data set. In statistics, when we consider the concept of Venn diagram, we have a universal set, say, and that universal set is always represented by using the capital letter U. Okay, but U means all data values under consideration, and that is the concept. So universal data set, the assumption is that it contains all possible data pairs of the form x, y, as well as their probability distributions. And probability distributions in the sense, I hope all of you are familiar with probability distributions. A number of different probability distributions are there, like binomial distribution, then Poisson distribution, then normal distribution, T distribution, chi-square distribution, etc., etc. Okay, but here in the concept of universal data set, our assumption is that it contains all possible data members, all possible data pairs of the form x comma y together with their distributions. Every data set follows a particular probability distributions. Then the collection of whole data plus the corresponding probability distributions actually defines the universal data set. Then for practical applications, we observed only a subset of the universal data set due to lack of memory and some other unavoidable reasons, because in our computer the memory is limited, so it is not possible to store all the data available in the world. So we always concentrated on a subset of the set of data, subset of the set of data. And the acquired data set is called the training data set. That means if there exists a valid subset of the universal data set, and that subset can be considered as the training data set. That means we are going to take the inference from the training data set. Then after that we can generalize. That is, this training data set is used to learn properties and knowledge of the universal data set, and that concept is actually known as generalization. Okay, but here we have a small data set, and that is the training data set. And from this training data set, we can extract various properties and knowledge or patterns. And these patterns, our assumption is that, or our conclusion is that, these patterns or these properties or this knowledge are actually the knowledge of the universal data set. And that concept is actually known as generalization. And this is the concept we followed in the case of inferential statistics. Okay. And vectors in the training set are assumed to be independently and identically sampled from the universal set, and that is known as sampling. That is also a concept of statistics. That means in order to build the training data set, actually the training data set is constructed from the universal data set, and by selecting the various instances independently and identically, and that the concept is known as sampling. That means with the help of a sampling technique, we can select various instances from the universal data set to construct the training data set. And in machine learning, the properties learned from the training data set actually explains the training set, and also used to predict the unseen samples. Unseen samples means, and that is actually known as the generalization. That means the knowledge obtained from the training data set can be applied to take decisions for a new unseen case. When a new patient came, by the knowledge extracted from an already existing data, the same knowledge can be applied for the new patient, because this new patient is an element of the universal data set. So, and our argument is that the knowledge obtained from the training data set is applicable to the universal data set also. So this knowledge can be applied to new unseen case, and that is the main idea behind any machine learning algorithm. Then, to examine the performance of learning, another data set may be reserved for testing, and that is called the test data. That is, once the learning is over, actually learning happens from the training data set, and learning is over, we have to evaluate the performance of that learned properties. And in order to measure the performance, we need another data set, and that data set is known as the test data. Okay, but here test set is unobserved during the training or learning process. That means at the time of training, and this data set is not visible to the learning algorithm. Test data is not visible to the learning algorithm. And after learning from the training data, we can submit this particular test data, and this as per the or when we input the test data into the learning algorithm, it generates some results. Then based on that results, we can measure the performance of the learned model. And in order to measure that performance, we have to reserve another small data set that is also a subset of the universal data set, and that data set is known as the test set. So this is the concept of the training data and test data. Training data is the information used to train an algorithm, and the training data includes both input data and the corresponding expected output. Expected output, that is label. Input data is there, features are there, and along with that features, label is also there in the training data. And this label is actually known as the ground truth. And based on this ground truth data, the algorithm can learn how to identify patterns to generalize the information contained in the data set, so that it can make accurate decisions when later presented with the new data. So, and here in the training data, the label is very important. That is actually that label represents the ground truth. Because this knowledge is generated based on the ground truth. For generalizing the information, this ground truth information or the label is very important, and that is the reason why we preserve the label in the training data set. But in the case of testing data or test data, on the other hand, includes only the input data. That is, features are there, independent variable values are there, X values are there, not the corresponding expected outputs. But that expected output is available in our hand, because we can compare. We can compare after generating the output using the test data. What is the output generated, and what is the difference between the output generated and the actual data, and that can be measured with the help of the information generated. So the test data is used to assess how well our algorithm was trained and to estimate the model properties. So that means after the training we get a model, then the performance of that model, to evaluate the performance of that model, we need a subset of the universal data set, and that subset is actually known as the test data. So the training data is used to make sure the machine recognizes the patterns in the data. That means in order to extract the knowledge, we need the training data. Then in addition to the training data, another set of data is also used for cross validation. Cross validation, that means it is actually a subset of the training data set. Then after each iteration, we have to evaluate the performance of the model at each stage of the iteration. And for that, we have to reserve a small amount of data from the training data, and that data is actually known as the cross validation data. And this cross validation data or the concept of cross validation is used to eliminate some undesirable properties of the machine learning algorithms, such as underfitting and overfitting. Or underfitting and overfitting, these are two undesirable properties of some machine learning algorithms, and these properties can be eliminated with the help of the cross validation data. And as I said earlier, the test data is used to see how well the machine can predict new answers based on its training. That means the performance of the model, and that performance of the model can be evaluated with the help of the test data. So here, the training data and test data, these two are very important in machine learning. Training data that can be used to extract the knowledge, and once that knowledge is extracted, then in order to performance of that particular model, we need another data set, and that data set is actually known as the test data. And these are the various types of machine learning algorithms. I already said the different types of machine learning algorithms, like supervised machine learning algorithms, unsupervised machine learning algorithms, semi-supervised machine learning algorithms, and reinforcement learning algorithms. And this classification is mainly based on whether or not the system is trained with data collected with human supervision or not. And with the help of a human supervision, we collect the data, and that data is always have a particular label. Because from the in a hospital, the last 10 years data, if we collect the last 10 years data, we can see that all the data elements are entered into the system with the help of some expert doctors. Okay, but here these doctors, it is the responsibility of that particular doctor to evaluate each and every patient visiting that particular hospital and assign a label. Label is nothing but the disease. And that type of data is available in any hospital. We can collect the data, and from that data we can extract some knowledge, and with the help of that we can take various decisions. Okay. Then supervised machine learning, because I'm going to concentrate only on supervised learning. And in supervised learning, training data feed to the algorithm is the labeled data set. And supervised learning tries to find the relationship between the feature set and the label set, which is the knowledge we can learn from the labeled data set. And that is very important in the case of supervised learning. But supervised learning tries to find the relationship between the feature set and the label set, and what type of relationship existing in between the disease and the features like symptoms, lab results, etc. And we can find out a relationship, and that relationship is actually known as the knowledge. And it is possible to represent that relationship with the help of some mathematical concepts. And if we are in a position to represent the relationship in a mathematical way, and that mathematical way of formulating that relationship is actually known as machine learning. And if each feature vector X corresponds to a label L, where L is equal to L1, L2, L3, etc., Lc, and C is usually ranged from 2 to 100, the learning problem is called classification. That means for each feature vector, and corresponding to that each feature vector, if we are in a position to map a particular label to that feature vector, then the problem can be considered as a classification problem. But here, if we have only two different classes, for example, if the disease, if the patient, again, if we consider the details of a patient database, and if the data set contains the information related to COVID-19 patients, whether that particular patient affected with COVID-19 or not affected with COVID-19. Okay, and that type of problem can be considered as a two-class problem. Okay, but here L contains only L1, L2. L1 is the first class and L2 is the second class. But in general, here we have C different classes, and C usually ranges from 2 to 100. And in that case, the problem can be considered as a classification problem. That means here from the data set, if we consider any instance from that data set, that instance can be mapped onto a particular label. So the problem is a classification problem. And a spam filter is a good example for a supervised machine learning task, that is classification. And it is trained with many example emails along with their classes. And class means this can be considered as a two-class problem. That is, the mail can be a spam email or a ham email. And here we have a data set. This is the training set. And this training set contains the characteristics of various emails along with the corresponding label. And from this training data set, we can find out the relationship existing in between the various features and the corresponding label. And with the help of that extracted relationship or extracted knowledge, we can take the decision regarding when a new email came, whether that email is a spam email or a harm email. That decision can be taken by using the relationship extracted from the training data set. And that is the idea behind any type of classification algorithms. That is, we can provide a training data set, there is a labeled data set, and from that labeled data set, we can extract some relationship existing in between the features and the corresponding label. And this relationship can be used for taking the decision regarding a new email. When a new email came, we can check whether that email is a spam email or not spam with the help of the learned relationship. But here, if each feature vector x corresponds to a real value, that is y belongs to R. In this case, y is not a real value, spam or harm. That is the label that can be given in this case. So this is not a real value. In some cases, the label may be a real value. Then, if the label is a real value, the learning problem is defined as the regression problem. As an example, to predict the target numeric value, say price of a car, given a set of features like mileage, age, brand, etc. That means we have a data set representing the details of some cars, and these are the features like mileage is one feature, age is another feature, then brand is another feature. A number of features are there, and when we provide these features to our machine learning model, this machine learning model generates a real value, say price of the car. Then in that case, the problem can be considered as a regression problem. But in our previous problem, this is not a regression problem, this is a classification problem. So classification and regression, these are two important important components in machine learning. Okay, supervised machine learning, classification and regression. But here, this is a classification problem. But if you consider this particular problem, this is a regression problem, because the label is a numeric value, not a categorical value. The knowledge extracted from supervised learning is often utilized for classification and prediction. And note that some regression problems can be used for classification as well, and vice versa, because here when we consider the simplest machine learning algorithm, that is linear regression. Linear regression is a regression problem, but this linear regression can be modified to classify some emails, and in that case that classification can be considered logistic regression. Logistic regression is a classification algorithm, and it is a modification of the linear regression. But here, that is the difference between regression and classification. Classification is always associated with some categorical values. Labels are categorical in the case of classification, but in the case of regression, the label is a numeric value. And in some cases, the regression problem can be modified to handle the classification.
Srija, please mute. Srija, one of the participant, please mute.
For example, logistic regression is commonly used for classification, as it can output a value that corresponds to the probability to a given class. That means in logistic regression, we can generate a probability. Even though it is a real value, it can be considered. For example, 0.2 is the value generated by that particular regression algorithm, and with the help of that real value 0.2, we can classify the email. That means there is a 20% chance that this particular email may be a spam email. Okay, and some of the popular supervised learning algorithms are linear regression, logistic regression, support vector machines, naive-Bayes classifier, then decision trees and random forest, neural networks. A number of other algorithms are also available. And in today's lecture, I'm going to implement the naive-Bayesian classification algorithm. And for that, in order to implement the naive-Bayesian classification algorithm, we have to understand, or we have to study some basic informations related to statistics like probability. That is one basic concept, probability. I think all of you know the concept of probability. So here the definition: consider a random experiment having n outcomes, and out of these n trials, an event A happens f times. Event A happens f times. And when we consider a random experiment, then the total number of outcomes can be considered as the sample space of that random experiment. I think all of you know the concept of a random experiment. Then out of these n trials, an experiment A happens f times. So A can be considered as an event. An event A happens f times. Then f by n is the frequency ratio of the event A. So based on that frequency ratio, the probability of that event can be defined in this way: P of A is equal to limit n tends to infinity f by n. And that is the actual definition of probability. So probability is always associated with a random experiment. Every random experiment is associated with a sample space. Then a subset of the sample space is known as the event. And here that event can be represented as A. Then f by n is the number of outcomes of the sample space. So f by n, and that is the frequency ratio of the event A. Then probability of A is equal to limit n tends to infinity f by n. Or simply P of A, the probability of the event A is equal to number of favorable cases divided by total number of outcomes. And that is the simplest definition of the probability: number of favorable cases, how many times they happens, divided by total number of outcomes. And this concept is very important in machine learning. The next, once again, to understand the concept of probability, the best example is flipping a coin. There are two possible outcomes. That means sample space contains only two outcomes, head or tail. And what's the probability of the coin shows the head when it is tossed. And all of you know, you can compute that probability. And what is the probability of the coin shows head when it is tossed? And here, here happens only one time. And how many sample spaces are outcomes are there? 2. So the probability is 1 by 2. That is 0.5. And again, another very important information is that the probability of an event is a number, always lies in between 0 and 1. The probability of an event is a number, always lies in between 0 and 1. And this is the basic information associated with the concept of probability. And I think all of you know now the concept of probability and sample space, event, then frequency ratio, then the definition of probability. Okay. The next very another important basic concept is conditional probability. Again, I think all of you knows the concept of conditional probability. The conditional probability of an event A, given that another event B has occurred, is denoted by P of A given B, and is defined as P of A given B is equal to P of A intersection B divided by P of B, where P of B not equal to 0. And this is a basic definition. I don't want to discuss more on this particular definition. I think all of you know the concept of conditional probability. But here, in the case of this conditional probability, P of A given B, the information regarding the event B, that is known to us. Based on that known information, how can we compute the probability of another event A? So probability of A given B is equal to P of A intersection B divided by P of B. And when we consider a Venn diagram, this is the representation of A intersection B. So this is A and this is B, this is A intersection B, and this can be represented as B intersection A complement, A intersection B complement, and all these informations we studied in our high school classes. Okay. Then And with the help of this conditional probability, to understand the basic concepts of conditional probability, we can consider a very simple example. If a fair die is tossed, then what is the sample space? Sample space S is equal to 1, 2, 3, 4, 5, 6. Because 6 different phases are there in a die. Let A be the event that the outcome is an odd number. Okay, then A, what are the possible cases of cases corresponding to this event A? That is 1, 3, 5. Because the event A is the outcome is an odd number. That is, when an odd number comes, then that can be represented as the event A. And these are the possible cases: 1, 3, 5. Also, let B be the event that the outcome is less than or equal to 3. Less than or equal to 3. That is, B is equal to 1, 2, 3. 1, 2, 3. Then and here we can I would like to ask two questions. And what is the probability of A? Then the second question is, what is the probability of A given B? What is the probability of A given B? Then, as per the definition of probability, what is probability of A? Number of favorable cases divided the total number of outcomes. And here, P of A, the number of favorable cases, that is the cardinality of A divided by cardinality of S, where S is the sample space. Then what is the cardinality of A? How many possible cases are there? In the case of A, how many possible cases? 1, 3, 5. That is 3. That is the number of possible cases there. That is favorable cases 3. Then total number of outcomes. Total number of outcomes. The total number of different information contained in the sample space. That is 1, 2, 3, 4, 5, 6. So 3 by 6. 3 by 6 is 0.5, and that is the probability of A. Now, let's find the conditional probability of A given that B has occurred. Given that B has occurred. And if we know B has occurred, the outcome must be among 1, 2, 3. Okay, because B is even B is defined as an outcome with less than or equal to 3. Less than or equal to 3. So for A to also happen, the outcome must be in A intersection B. That means A and B simultaneously should occur. Then in that case, A intersection B is equal to 1, 3, because A is 1, 3, 5 and B is 1, 3, 1, 2, 3. So A intersection B is definitely 1, 3. Then and here all the outcomes are equally likely. All the outcomes are equally likely. That means the chance of occurrence is same for all the different outcomes. All the different outcomes. So in that case, probability of A intersection B, as per the definition of probability of A given B, it is the cardinality of A intersection B divided by the cardinality of B. That means how many outcomes are there in A intersection B? Only 2 outcomes. Then how many outcomes are there in B? In B, the outcomes are 1, 2, 3. So 3 outcomes, therefore 2 by 3. So probability of A given B is equal to 2 by 3. And this A given B is nothing but this information is available in our hand. The information regarding B is available in our hand. Based on that, we can take the information regarding another event A, and that is actually P of A given B. And in this case, P of A given B is equal to 2 by 3. In this way, we can solve some simple problems related to conditional probability. A number of other problems are also there. Then, next, we can move on to another very important basic concepts of probability, that is Bayes' theorem, because this is a very important concept in probability theory. Bayes' theorem was named after 18th century mathematician, that is Thomas Bayes. And Bayes' theorem relies on incorporating prior probability distributions in order to generate posterior probabilities. Then what is actually the prior probability and posterior probability? And this is very important in Bayes theorem. Then prior probability is nothing but is the probability of an event before new data is collected. Before new data is collected. That means from the data available from our in our hand, some data values are there, and if we generate a probability from that existing data, and that probability can be considered as the prior probability. So prior probability in Bayesian statistical inference is the probability of an event before new data is collected, or before occurring a new event, before occurring or before adding a new information. If we take some probability values, then these probability values can be considered as the prior probability values. Prior probability values. And the posterior probability. What is the posterior probability? The posterior probability is the revised probability of an event. Revised probability of an event occurring after taking into consideration the new information. New information. But here, posterior probability is the revised probability of an event occurring after taking into consideration the new information. That means, if, for example, if we consider two different events like A and B, the information regarding the event B is known to us. Then, if we compute the probability of event A by considering the event B, then that type of information can be considered as the posterior probability. Okay, and that is the meaning of posterior probability. And if we compute the probability of A alone, if we compute the probability of A alone, and that can be considered as a prior probability. And instead of that, if we consider the probability of A given B, and that type of probability can be considered as a posterior probability, because in the case of posterior probability, we add some new information, like a probability of A given B based on the event B. If we are in a position to take the decision regarding A, then that type of decisions is an example for posterior probability. Then again, we know that the joint probability means the probability of A intersection B. Okay, and that is commutative. For example, if we consider two different events A and B, we know that P of A intersection B is equal to probability of B intersection A. So intersection is commutative, and we already studied all those properties in our mathematics classes. So P of A intersection B from the conditional probability, and from the definition of conditional probability, probability of A intersection B is equal to P of A into P of B given A. Because what is P of A given B? P of A given B is P of A intersection B by P of B. And from this expression, what is P of A intersection B? P of A intersection B is P of A given B into P of B. Okay, but here P of A intersection B is equal to P of A into P of B given A. Similarly, P of B intersection A can be calculated as P of B into P of A given B. Okay, but from this commutative property, we know that P of A intersection B is equal to P of B intersection A. So we can equate these two expressions, that is P of A into P of B given A, and P of B into P of A given B. So from this expression, P of A given B can be computed as P of A into P of B given A divided by P of B, where P of B not equal to 0, and this is actually the concept of Bayes theorem. So here this posterior probability P of A given B can be computed by using P of A. P of A is a prior probability, P of B is also a prior probability, and P of B given A is another posterior probability. That means if these three informations are available, and based on this, we can generate another posterior probability A given B as P of A into P of B given A divided by P of B. And this is actually known as Bayes theorem, and this Bayes theorem is very important in machine learning. Bayes theorem is very important in machine learning. Then, in order to explain the concept of Bayes theorem, we can consider a very simple example. Suppose you might be interested in finding out a patient's probability of having liver disease if he is an alcoholic patient. If he is an alcoholic patient. Okay, but here being an alcoholic is the test of liver disease. And let A be the event that patient has a liver disease. Patient has a liver disease. Okay, then past data tells you that 10% of the patients entering the clinic have liver disease. That means this is a prior probability, and that is P of A is equal to 0.10, and this is a prior probability. And this information is available in our hand. This information is available in our hand. And let B, another event, let B could mean that the patient is an alcoholic patient. Patient is an alcoholic patient. Then past data shows that 5% of the clinic patients are alcoholics. Okay, again from the clinical database, we can compute that the 5% of the clinics patients are alcoholic. That means P of B is equal to 0.05. This is also a prior probability, because this probability can be directly computed from our data set. Then you might also know that among those patients diagnosed with liver disease, 7% are alcoholics. That means here again, if we analyze the past data from that clinic, we can infer that 7% of the time, if a particular patient is identified as a liver disease patient, then that patient is always a alcoholic patient, and 7% of the time this argument is true. 7% of the time this argument is true, and that is the meaning of this particular statement. Among those patients diagnosed with liver disease, 7% are alcoholics. And this is actually our posterior probability that is directly calculated from the that can be directly calculated from the given data set, and that probability is nothing but probability of B given A. B given A, that is the probability that a patient is alcoholic given that they have liver disease. That is 7%. But here A represents the information regarding the liver disease, and that information is given. That information is available in the clinic data set. Then here actually we are computing the probability that what is the probability of that particular patient is alcoholic patient given that he has liver disease. So this information is probability of B given A, and that is 7% means 7% means that is 0.07. That is a probability of B given A. Then but here all these informations can be computed from the clinic data set. Clinic data set, P of A can be computed, P of B can be computed, P of B given A can be computed, and this information can be directly applied for taking decisions like for example, we must find out a patient's probability of having liver disease if he is an alcoholic patient. Suppose a new patient came, and we have an information that that patient is an alcoholic patient. That means with the help of some test, we can identify whether that particular patient is a alcoholic patient or not. Some testing procedures are there, and with the help of those procedures, we can measure whether that particular patient is an alcoholic patient or not. Okay, but here we have an information, and as a result of that test, we have the information that that particular patient is an alcoholic patient. Then we have to calculate and what is the probability of that particular patient is has a liver disease, and given that that particular patient is an alcoholic patient. So in order to take a decision, For example, P of A given B, that can be considered as a decision. But here B can be considered as a symptom, and the value of that symptom is known to us. Based on that known information, we can take the decision that probability of A given B. But here, while calculating this information, probability of A given B, there comes the importance of Bayes theorem. Bayes theorem. So, as per the Bayes theorem, we can compute the probability as probability of A given B is equal to P of A into P of B given A divided by P of B, and that is the usual equation. And here P of A is given, that is 0.07, 0.10. P of B given A, that is 0.07, and P of B is 0.05, I think. Okay, but here 0.07 into 0.1 divided by 0.05, so 0.14. That is probability of A given B. And what is the interpretation that can be given for that probability of A given B? The interpretation is that if the patient is an alcoholic patient, their chances of having liver disease is 0.14. That is 40% of the time this particular patient has liver disease, since this patient is an alcoholic patient, and that is the information obtained from this particular probability. And these type of decisions we can take with the help of Bayes theorem. And in machine learning, we can use this Bayes theorem for taking a lot of efficient decisions, and there is a specific classification problem or classification algorithm is there, and the name of that algorithm is actually known as the Bayesian classification algorithm. Then now, when we consider the naive Bayesian classifier, in order at the time of implementing that Bayesian classification algorithm, we have to consider some assumptions. By incorporating those assumptions, the Bayes theorem can be modified as naive Bayes classifier. So naive Bayes is a supervised learning algorithm for classification. So the task is to find the class of observation or data point given the values of features. Okay, that means if we have feature values, based on these feature values, we have to take a decision regarding whether the particular patient is a liver disease patient or not. Some feature values are there. It's an alcoholic patient. He has temperature, muscle pain, etc., etc. A lot of symptoms are there. Based on these symptoms, we have to decide whether that particular patient is a liver disease patient or not. Then, in that case, this naive Bayes classifier calculates the probability of a class given a set of feature values. That means we have to compute the label yi given x1, x2, x3, etc., xn. These are the symptoms and lab results. Based on these symptoms and lab results, and these symptoms and lab results are known to us. Based on those known values, we have to take the decision regarding that disease. And it can be symbolically represented in this way: probability of yi given x1, x2, x3, etc., xn. And when we input this information into the Bayes theorem, and what is Bayes theorem? Bayes theorem actually states that P of A given B. But here B is x1, x2, x3, etc., xn. A is yi. yi given x1, x2, x3, etc., xn is equal to probability of yi into probability of x1, x2, x3, etc., xn given yi divided by probability of x1, x2, x3, etc., xn. Okay, that is when we substitute this information into the Bayes theorem, the Bayes theorem becomes probability of x1, x2, x3, etc., xn given yi into probability of yi divided by probability of x1, x2, x3, etc., xn. Then how many components are there in this formula? This is the first component, probability of x1, x2, x3, etc., xn given by yi. That is the first component. Probability of yi, that is the second component. Then third component is probability of x1, x2, x3, etc., xn. Okay, but here probability of x1, x2, x3, etc., xn given yi means the probability of a specific combination of features given a class label. That means if this patient from the past data, if we inferred that if the patient is a liver disease patient, then what are the values of these symptoms? What are the values of these symptoms? And this information can be directly obtained from the data set. So probability of x1, x2, x3, etc., xn given by I means the probability of a specific combination of features given a class label. Given a class label, that is, this class label is available. So this information can be directly obtained from the data set itself. And to calculate this, we need extremely large data sets to have an estimate on the probability distribution for all different combinations of feature values. And that is a requirement. That is a requirement for computing this probability. We need extremely large data sets. Then only we can generalize that information. Otherwise, the information may not be correct. Otherwise, the information may not be correct. And again, we need the probability distribution for all different combinations of feature values. All different combinations means x1, x2, then x1, x2, x3, then x1, x2, x3, x4, etc. That type of combinations given by I. That type of combinations are necessary for computing that probability. And it is a very difficult and challenge in the case of a large data set. And to overcome this issue, Naive-Bayes algorithm assumes that all features are independent of each other. That means these feature values, features are independent, x1, x2, x3, etc., xn. These are the features, and in the case of Naive-Bayesian algorithm, we assume that all these features are independent. That means x1 does not depend on x2, x2 does not depend on x3, x1 does not depend on x3, and so on. These are independent features. Okay, but here with the help of that particular assumption that all these features are independent, this probability can be computed as this probability, that is p of x1, x2, x3, etc., xn given by I, that can be computed as probability of x1 given by I into probability of x2 given by I, etc., probability of xn given by I. Then what is this? Probability of x1 given by I. If the patient is an alcoholic patient, then what is the probability of satisfying this particular symptom corresponding to this disease? That is yi. And this probability of x1 given by I can be computed from the data set. How many times when alcoholic patient, in the case of alcoholic patient, this particular symptom occurs, that can be directly computed from the data set. Then probability of x2 given by I for an alcoholic patient, for a liver patient, liver disease patient, how many times this particular symptom satisfied in that case. This probability can be directly computed from the data set. Similarly, for the liver disease patient, the nth symptom, how many times that nth symptom occurs in the data set. So this information can be very simply calculated from the given data set. So when we take the assumption that the symptoms x1, x2, x3, etc., xn, all these symptoms are independent symptoms, then by considering that particular assumption, the numerator of that particular formula can be changed into probability of x1 given by I into probability of x2 given by I into probability of x3 given by I, etc., probability of xn given by I into p of I. P of I, again, that is a prior probability. We can directly compute from the data set itself. Then again, the denominator is probability of x1, x2, x3, etc., xn. This is actually a constant value, and this can also be obtained from the data set itself. That is probability of x1, x2, x3, etc., xn. And if x1, x2, x3, etc., xn is independent, then the probability of x1, x2, x3, etc., xn can be computed as probability of x1 into probability of x2 into etc. into probability of xn, and this is a fixed value. But in order to take the decision regarding this particular probability, there is no need of this denominator value. No need of this denominator value, because this probability calculation, probability of yi given x1, x2, x3, etc., xn depends only on the numerator. Depends only on the numerator. But here, probability of yi can be computed in this way: number of observations with class yi divided by the total number of observations. And with the help of this information or this formula, we can directly compute probability of yi, because probability of yi is a prior probability. And the probability of x1, x2, x3, etc., xn given by I can be computed in this way: probability of x1 given by I, probability of x2 given by I into etc., probability of xn given by I, and all these probabilities can be computed from the data set itself. But here, the algorithm needs to store probability distributions of features for each class independently, and if that the distributions of the probability distribution between x1 and yi. X1 is the feature and yi is the corresponding label, and if we are in a position to understand the distribution or the probability distribution corresponding to x1 and yi, for example, x1 follows a normal distribution. Then this probability of x1 given by a can be computed from the probability density function of that normal distribution. And what is the probability density function of a normal distribution? 1 by sigma root of 2 pi into e raised to minus x minus mu the whole squared divided by sigma squared. And here mu represents the mean and sigma represents the standard deviation of the population. So if we have the mean and standard deviation of the normal distribution, and if this x1 follows a normal distribution, this probability can be directly computed by using the probability density function of the normal distribution. So this computation is very easy. But here, instead of storing the data set, if we know the distributions satisfying all these features, it is better to store the these distributions instead of storing the data values. So the algorithm needs to store probability distributions of features for each class independently. So independent probability distributions we have to store instead of storing the whole data. For example, if there are 5 classes and 10 features, around 50 different probability distributions we need to store. That means 5 classes and 10 features. But here, if we consider the first feature, then first feature follows class 1, or first feature follows class 2, or first feature follows class 3, and so on. Okay, but here around, in this case, around 50 different probability distributions we have to store. Okay, and the type of distributions depends on the characteristics of features. Type of distributions depends on the characteristics of features. And for example, if the features are binary features, that means if the features accept only the binary values like yes or no or 0 or 1, then in that case we can say that that type of features follows Bernoulli's distribution, that is binomial distribution. And for discrete features, that is words of counts, we can directly say that that particular feature follows multinomial distribution. And for continuous features, that means x1, x2, x3, etc. takes continuous values, then we can directly say that that particular those features follows Gaussian or normal distribution. And again, another very important or a very interesting fact is that in our real world, around the same 70% of the data follows normal distribution. That means if we consider any data set, and if we consider various features from the data set, we can see that around 70% of the features follows normal distribution. So the normal distribution is very important. You have to study about the properties of the normal distribution to study about the machine learning. Because most of the time we have to apply the concept of Gaussian or normal distribution for getting the correct decision from a machine learning algorithm. So Gaussian or normal distribution is very important. And this is the first part of my lecture. And in this particular lecture, we discussed some basic concepts of different type of data sets, labeled data, unlabeled data, etc. All these things we have discussed. Then we discussed some basic concepts of statistics like probability, then conditional probability, then Bayes theorem, then how Bayes theorem can be used for decision making. This is the first section of my lecture, and in the second section, after 5 minutes break, we can continue the next section. And in the next section, I am going to discuss the implementation of the Bayesian classification algorithm with the help of a very simple data set, a very small data set. We can take a very small data set, and by using Python or various facilities available in scikit-learn library, how this naive Bayesian algorithm can be implemented. That is my second in the second session we can discuss this information. So after a 5 minutes break, we will discuss all these things. Okay.
Participants, please stay back and have the second session, which will be very effective for you. Thank you.
Hello. ഞാൻ ക്ലാസ്സില സർ. ഓക്കെ. ഹലോ ബിനുമോൾ. ഹലോ. എന്റെ സ്ലൈഡ് കാണാമോ?
കാണാം. There is
Okay.
a question in the chat.
Okay.
Teacher.
Yes, yes.
Consider it.
What is the question?
How could sentimental analysis be used using naive Bayes algorithm?
Which one?
How could sentimental analysis?
Yes. And after this discussion, we can take those that type of questions. Okay. 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 Hello, Binamol. Hello, Binamol.
Guys, welcome
Okay.
back.
Okay. Thank you. And example and implementation. And in order to implement the concept of Bayes theorem, we can consider a very simple data set, very simple data set. And here in this data set, we have three different features like color, type, origin, and this is the label associated with the data set. And here this information is associated with a car data set. If the color of the car is red and the type is sports and origin is domestic, stolen is equal to yes. That means there is a possibility to store possibility that the cars may be stolen. Okay, then if the color is red, type is sports, origin is domestic, there is a possibility that there is no possibilities to stolen that particular car. Okay, anyway, this data set is only an example data set. Maybe some uncertainties there, inconsistencies there. Actually, these two rows are inconsistent in the reality. These two rows are inconsistent because same set of features but different decisions. But different decisions, and in a real life environment, these type of inconsistencies are not possible. But when we collect a data set, for example, in the case of a patient data set, there may exist some inconsistencies. But using Bayes theorem, we can consider these inconsistencies very efficiently. So these are the independent variables, color, type, and origin. These are the independent variable, and this is the dependent variable or the label. So we have three features, and these are the values of the features. So 10 different car details are available in the data set. So the problem is, suppose we want to classify red SUV domestic using new Bayes classifier. That is our question. If a new car came and the color of the car is red, then the type, second I think type is SUV, and the origin is domestic. Then what is the probability of this car may be stolen? Or stolen is equal to yes. What is the probability that stolen is equal to yes, or what is the probability that stolen is equal to no? Then based on these two probabilities, we can take the decision regarding the chance of stolen. Okay, then in order to compute that, so here we have to given that probability of stolen, given color is equal to red, type is equal to SUV, and origin is equal to domestic. We have to compute that probability, and in order to compute that probability, what we need? So here, in this case, we have to compute two different probabilities. The first probability we have to compute is probability of stolen is equal to yes, given color is equal to red, type is equal to SUV, and origin is equal to domestic. Then second, we have to compute the probability that stolen is equal to no, given red SUV domestic. And these two probabilities we have to compute. Then comparing the probability values, we can take the decision. Then in order to compute the probabilities, we have to generate these prior probabilities. Probability that stolen is equal to yes. This prior probability can be directly computed from this table. How many yes values? Stolen is equal to yes1, yes2, yes3, yes4, yes5. 5 stolen is equal to yes values are there. So probability that stolen is equal to yes is equal to 5 divided by 10, because 10 different instances are there. So 5 by 10 is equal to 1 by 2. Then similarly, we can compute probability that stolen is equal to no. stolen is equal to no. No. 5 times no is there. So again that probability is equal to 1 by 2. Then probability that red given stolen is equal to yes. That means when we can consider stolen is equal to yes, among these stolen is equal to yes, how many red is there? How many color is equal to red is there? That is yes red 1, then yes red 2, then yes red 3. Okay, 3 red values among these yes values. So that probability red given stolen is equal to yes is equal to 3 by 5. Then probability of red given stolen is equal to no. Similarly, we can compute the probability that is equal to 2 by 5. Similarly, probability of SUV given stolen is equal to yes 1 by 5. Probability of SUV given stolen is equal to no is equal to 3 by 5. And probability of domestic given stolen is equal to yes is equal to 3 by 5. Probability of domestic given stolen is equal to no is equal to 3 by 5. But these are the probabilities. We have to compute the above probabilities. We have to compute the above probabilities. So now we are going to compute separately the probabilities for this car to be stolen via safe. Stolen was safe, or stolen is equal to yes versus stolen is equal to no. And that is first we compute probability that stolen is equal to yes given red SUV domestic. And what is the probability? When we apply the Bayes theorem, the probability, the formula is probability that stolen is equal to yes given red SUV domestic is equal to probability of red given stolen is equal to yes into, because our assumption is that in Bayesian classification, our assumption is that all these features are independent. All these features are independent. So probability that red given stolen is equal to yes into probability that SUV given stolen is equal to yes into probability of domestic given stolen is equal to yes into probability of stolen is equal to yes. Probability of because the actual formula is probability of x1 given y1 into probability of x2 given y1, etc. Probability of xn given yn into probability of y1 divided by probability of x1, x2, x3, etc. xn. But denominator, there is no need of considering the denominator. But so we consider only the numerator part. So in the numerator part, we have to consider probability of red given stolen is equal to yes into probability of SUV given stolen is equal to yes into probability of domestic given stolen is equal to yes into probability of stolen is equal to yes. And when we compute this, that is, all these values are the when we consider these values, and all these values we already computed independently. So 3 by 5 into 1 by 5 into 3 by 5 into 1 by 2. 1 by 2, therefore 9 divided by 250. That is the probability. And which probability? Probability that stolen is equal to yes given. Okay, red SUV domestic. Next, we have to compute probability of stolen is equal to no given red SUV domestic. Similarly, we can compute. There is only a small change in that particular information because here stolen is equal to no. So similarly, when we compute that probability, we get the value 18 by 250. So when we compare these two probabilities, we can see that this probability is higher compared to this probability, and this probability corresponds to probability of stolen is equal to no. So when we consider these feature values, red SUV domestic, this car may be safe because of these feature values, that is red SUV domestic. And that is the interpretation of these two probabilities, because this probability is higher than this probability. That means there is no chance that this vehicle is stolen by somebody else. Okay, so that is the decision obtained from this particular problem. So this type of decision making task can be very effectively solved with the help of Bayesian classification. Now we can implement this Bayesian classification with the help of scikit-learn. I think all of you are aware with Python programming. Python programming, and in that Python programming language, there is a specific library known as scientific Python. Scientific Python. So that means for computing the for performing scientific computations, we can make use of this particular library. And scikit-learn provides provides a lot of functionalities, and some of the functionalities I am going to use in this particular implementation. So before writing the program, we have to import the necessary libraries first. Then import pandas as PD, pandas, and that can be considered as a data structure in Python programming language. Data structure, that is here data frame. Data frame is a very important data structure in Python, and I think you are familiar with data frame and the arrays, two-dimensional arrays, because there is a slight difference between the data frame and array. And in the case of data frame, each column of a data frame can be considered as a table, but in the case of a data frame, we can label each column and each row of this particular table, and that is the advantage of a data frame. But in the case of a two-dimensional array, it is not possible to label the columns and rows. Again, if you consider the database management system in the concept of a table, okay, and each column of the table can be labeled with the help of the attribute name at the time of defining the table itself. That is create table. When we use that create table command, we can specify the column name there. But in the case of two-dimensional arrays, there is no need of that means there is no chance of specifying a label for the columns and rows. But in the case of data frame, we can specify the labels for rows and columns. So the first import statement is import pandas as PD, and this pandas means in order to work with a data frame, we need some functionalities, and all these functionalities are available in pandas. Then another important library we need, that is from sklearn import datasets, because here I am going to use an example dataset, and this example dataset is an experimental dataset available in Python itself, and Python provides a number of different experimental datasets, and all these datasets are available in a particular library, and that library is known as datasets. We have to incorporate that dataset library into our program, and for that we can make use of this particular statement from sklearn import datasets. Then from sklearn.metrics import confusion metrics. That means while training the algorithm, we have to measure the performance of the learned model, and for that that performance can be evaluated with the help of a facility, and that facility is known as the confusion metrics. And in order to use this confusion metrics, you have to import that, and for that we have to use this particular statement from sklearn.metrics import confusion metrics. Then another important library, that is from sklearn.model selection import train test splitter. But here train test splitter, and we can generate the training data and test data automatically with the help of a functionality, and that functionality is nothing but train test splitter. So in order to use this train test splitter, we have to import that particular functionality into our model, and for that you can use this statement from sklearn.model selection import train test split. Then first of all, you have to load the data set, and here I am going to use iris data. Sorry, not iris data, diabetic data. There's a small mistake in this comment statement. Loading the diabetics data set. Loading the diabetics data set, and for that we can make use of, in order to load that data into our program, we can use this particular statement. Data set is equal to pd dot read CSV, because I am going to load the data and that file format followed by that particular data set is CSV format. File format is CSV, that is comma separated value format. This is Excel format. And right now I just download this diabetic data set from the internet, and in my desktop, this diabetics data set is available in CSV format. And in order to load that data set into an object named dataset, you can use this particular statement. The dataset is equal to pd.csv. pd means that is an object of this pandas library, and this pandas library provides a lot of functionalities. Read CSV is one such functionality. To read a CSV file, we can make use of read CSV, and here along with the path you can specify the file name. Okay, then next statement is dataset.head. Using this functionality, using this method, we can display the first 5 records of the loaded data. First 5 records of the loaded data, that is dataset.head, to evaluate whether the to check whether the dataset is available in my system. And in order to check that, or in order to evaluate that, we can make use of this dataset.head. So when this particular statement is executed, dataset.head is executed, this is the outcome obtained, first 4 records. And when we go through the records, we can see that these are the features: pregnancies, glucose, blood pressure, skin thickness, insulin, BMI, database, pedigree function, age, outcome. This is the label associated with each instance. But here the first instance is mapped on an outcome 1. That means the patient is a diabetic patient. Second instance is associated with label 0. That means the patient is not a diabetic patient. And in this, this is the organization of the data set. This is the organization of the data set. So here now this is another feature. That means from the data set we can extract the feature columns. That is pregnancies, glucose, blood pressure, skin thickness, insulin, BMI, diabetes, pedigree function, age. Okay, that means all the feature columns we can extract, or feature names we can extract, and this is actually used for feature selection. And for example, in a particular environment, we don't want to include a particular feature BMI in this particular model building. In that case, while defining feature columns, you can eliminate BMI from this list. So in that case, BMI, that feature can be very easily eliminated from the feature set. Okay, but here based on these feature columns, we can extract all the values associated with feature columns by using this particular functionality, that is dataset of feature columns. All feature values are copied onto X. X now can be considered as a 2-dimensional array. Then Y is equal to dataset dot outcome. Outcome means that is the label. Outcome means that is the label. So Y is equal to dataset dot outcome. All the values of the labels that can be accessed with the help of dataset dot outcome. So here the total dataset is divided into 2: the set of all features, the set of the label. Okay, all feature values are now available in X. All label values are now available in Y. And now we can check whether the feature array X contains the necessary data values. For that, we can again make use of X.head. Okay. Now we can print the shape of X. That is, how many rows are there, how many columns are there. That information we can print with the help of X.shape. That is, this X.shape output the number of rows and number of columns of X. Then after separating X and Y values, we can split the data set into training data and the test data. And for that we can make use of this functionality, train, test, split. And this functionality is already incorporated into our program. Train, test, split with parameters x already derived, y, that is label set, random state is equal to 0. That is a random state. Actually, in the beginning of my lecture, I already discussed about sampling. But here we have the training data and test data. Actually, training data and the test data is created from the original data set. Then what are the instances that is to be included in the training data, and what are the instances included in into the test data, and that is actually selected randomly with the help of a seed value, and this seed value is used because if this random state is equal to 0 is not used in this particular implementation, what will happen is at each execution of the algorithm, it takes different instances at the time of creating X train and X test. But when we use random state argument, at each execution of the algorithm, the same training data and the test data is generated at each execution of the algorithm, and that is the importance of random state is equal to 0. Anyway, the training data and test data can be over here x values of the training data, and this is the x values of the x test data. This is the label for the training data. This is the label for the test data, and these are the 4 matrices that can be generated by using the train test split. And inside the train test split, the parameters are x comma y comma random state is equal to 0. These are the parameters, and these parameters are very important. Then now, first of all, we have to build the model. And for building the model, the corresponding functionality, because this Gaussian nairbase is already implemented in the scikit-learn library. We have to incorporate that particular facility into our program, and for that we can make use of this particular statement from sklearn.nairbase import Gaussian nairbase, because corresponding to nairbase, a number of different implementations are there. From among those implementations, I am going to use one such implementation, and that implementation is Gaussian nairbase. That means this implementation uses normal distribution to generate the probability. For computing that probability value. It uses the normal distribution, the concept of normal distribution. And the model building is very simple. After executing this particular statement, this Gaussian nairbase, okay, and that particular class is available in our program, and based on that class, we can create an object, and the object name is GNB. And for creating that object, you just use this particular syntax, Gaussian NB, and that is a function, and that is a method. And with the help of that method, we can create this object. So our model is now available in this object, and in order to train that model, another functionality is available in the sklearn itself, and that functionality is nothing but dot fit with parameters x train comma y train. So here it can be divided into 2 different statements. The first statement, you can divide this single statement into 2. First statement is GNB is equal to Gaussian nairbase. Then after that, GNB is equal to GNB dot fit. That statement is also will work. No problem for that. Anyway, the model definition and the training combined together with the help of this particular statement. So GNB is equal to Gaussian nairbase. So model is defined there. The same model can be trained with the help of the fit method. That is very important. That is a keyword. That is a method. With the help of that method, along with the parameters x train and y train. X train and y train means the training data. X train, y train actually represents the training data. So this training data can be used for train the algorithm Gaussian nairbase, and the model is now available in GNB. Okay, so this particular statement actually defines our model and train our model together. Okay, GNB is equal to Gaussian neighbors dot fit x train comma y train. Then once the model is built, once the model is available, we can measure the performance of that model. And before measuring the performance of the model, first of all, we have to generate the predictions corresponding to the test data. And for that, we can make use of another dedicated functionality, and that functionality is known as predict X test. But here there is no need of providing y test, because y test is used for comparing the performance. But in order to generate the prediction, there is no need of providing the label set. You have to consider only the feature set. We have to consider only the feature set. So GNB predictions is equal to GNB dot predict. Like fit, here we can use predict. Parameter is X test. And when we provide this X test with the help of the knowledge generated using this particular model, we can predict the different labels corresponding to X test, and all these labels are now available in GNB predictions. So in this particular slide, three different activities are included here. Model is defined, model is trained with the help of it method, and the prediction corresponding to X test is generated in GNB predictions. Then now we can compute the performance of that model. And for measuring the performance of the model, I am going to use a metric known as accuracy, and accuracy is equal to GNB dot score. Hello. Accuracy is equal to GNB dot score X test comma Y test. So here, in order to compute the accuracy, we can use this functionality, that is score. But when we use score, we have to use these two parameters together, that is X test, Y test. Using the X test, our model predict the performances. Then by comparing the generated result with Y test, it can compute the accuracy. And when we use X test and Y test in score method, it computes the accuracy as 0.765625. But here, using this particular functionality score, we can directly compute the accuracy. And the score method works in this format. Using X test, it actually computes the predictions first. Then the prediction is compared with Y test. How many predictions are real predictions? And for that type of a comparison, we can make use of Y test. Then based on that comparison, we can compute the accuracy. So that accuracy will print this value 0.765625. So this is the performance of our model. In this way, we can evaluate the performance of our model. That is one method. Another method is by creating a confusion matrix, we can measure the performance of the model. And for creating the confusion matrix, we generated the predictions before this particular slide. Okay, GNB predictions. So in order to generate the confusion matrix, we have to pass these two parameters. Y test is obtained from the test data. GNB predictions, we already generated these GNB predictions. So this GNB predictions can be obtained from that particular predict method. So these two values can be used as arguments in this method, that is confusion matrix. Okay, but here in this confusion matrix, when we pass these two arguments, it will generate a matrix like this. Okay, up here, this is a two-dimensional matrix, 114, 16, 29, 33. Up here, this is a two-class problem. Up here, this 114 actually represents the true positive classification. True positive classification. That means how many S values are mapped onto S. Okay. Then this represents how many S values are mapped onto no. Okay. Then this represents how many no values are mapped onto yes. Then this represents how many no values are not mapped onto no. Okay, because this is a two-class problem. So this when we consider the diagonal entries of this matrix, and that gives the correct predictions. Correct predictions, and from this confusion matrix again we can compute the accuracy as 114 plus 33 divided by 114 plus 16 plus 29 plus 33. That is the accuracy value, and when we compute that accuracy we get the same value as 0.765625. So from the confusion matrix also we can compute the accuracy. So, but in order to use the facility confusion matrix, we have to first generate the predictions. Then actual values are available in our hand. These two informations can be treated as arguments in confusion matrix. We can print this matrix. Okay, and that is the performance of the model. But here 76 or 77% of the time my model gives accurate results. Then another very important use of this particular model is, and actually this model is used to detect whether a particular patient, a new patient came, we have to check whether that particular patient is a diabetic patient or not. That is our aim of developing this model. So for that, if a particular patient came, we can measure the attribute values first. Okay, and this is the value of the first feature, this is the value of the second feature, third feature, fourth feature, etc. All feature values we can measure, and we can treat it as an array. Okay, but here after that we can convert that particular array into the required format needed for this particular algorithm. So for that x1 is equal to np dot as array of x1. Then after that, after generating this particular structure, we can consider this variable x1 as an argument in predict method. Okay, but here new is equal to GNB dot predict of x1. Predict of x1. This will give the prediction corresponding to this patient x1. This patient x1, and that prediction can be printed with the help of print new, and it will print 1. That means this patient is a diabetic patient. In this way we can take the decisions. This is actually the use of this particular model. That means when a new patient came, we can measure the values of all these symptoms. We can formulate all these symptoms as an array, and after that, that array variable can be used in the predict method. We can generate the predictions. That is about this particular model. Anyway, thank you all for hearing me patiently and the great support given to me during my lecture. Once again, I extend my sincere gratitude to all the faculty members of the department for giving me this wonderful opportunity. Thank you very much. Thank you, Binimol.
Thank you, sir.
If you have any questions, you can raise the questions, sir. No problem.
The teacher has left the session.
Okay.
A data set is given about utility fraud detection. I have built a classifier model and
Okay.
achieved a performance score of 98.3%. Is this a good model?
Pardon?
A data set is given about utilities fraud detection.
Okay.
I have built a classifier
Okay.
model and achieved a performance score of 98.3%.
Oh, that's a very good model. 98% or 98.5%, that is a very good classification accuracy. So that particular model can be considered as an efficient model. No problem for that.
Okay. Thank you, sir. Now, as the time has more than 4 o'clock, now let me invite Danya Mohan, Assistant Professor of Computer Science, to say out of thanks. Thank you, sir.
A very good afternoon to all. This webinar on decision making, a machine learning approach organized by Department of Computer Science, KKTM Government College, Kullu, in association with Department of Computer Applications, USAT, and also released our IT magazine, Tech Reports 2020, and it's a matter of great pleasure for our department in particular, for our college in general. My onerous duty is to extend our profound gratitude to all the people who had made this program a great success. From the bottom of the heart, I extend a sincere word of debt to our principal, Dr. Nesi EA, who had helped in numerous ways in organizing our webinar and magazine release. Dr. Sabu MK is a well-known scholar in computer science and professor and head of Department of Computer Applications, CUSAT, and on our request, he enthusiastically consented to speak to us on decision making, a machine learning approach. It's my privilege to record our sincere gratitude to him. Thank you, sir.
Thank you.
A special word of gratitude goes to Mr. Abhishek and Mr. Adarsh, who are the magazine editors, who have done a wonderful work in compiling the IT magazine. Srimati Binimol TV is our department head, and she is also a leading light, and no amount of praise is enough to her dedication to the department. On this occasion, as a formality, I thank her. Thank you, ma'am. It also gives me a great pleasure to thank all the teachers from other colleges and research scholars and students who participated in the webinar to make it a grand success. Thank you. Once again, thank you all.
Thank you, sir. So let me stop the session. Thank you all for